We need to show that this surface integral equal to negative of this volume integral, where S is a closed surface enclosing a region V and R equal to this. Now since R equal to square root of x square plus y square plus z square, so on squaring both sides we get R square to be equal to x square plus y square plus z square. Very fine. Okay. Let me derivate this with respect to x. So this is 2r partial derivative of r with respect to x equal to 2x. So these two cancelled out and we are getting the partial derivative of r with respect to x to be x divided by r. Right? Now because I need to get the ratio 1 by r, here also I am having 1 by r. And on the right hand side also I am having this 1 by r. So let's consider xi to be equal to 1 by r. Then del xi becomes del of 1 by r. Yes. Del xi means the gradient of xi. So finding this further, this is equal to, I am writing in the summation format. This is summation I vector partial derivative of 1 by r with respect to x. Right? And now we have to derivate this with respect to x. We are getting the summation I vector, we have to derivate 1 by r with respect to x. So we get negative 1 by r square into partial derivative of r with respect to x. Yes. So this is negative 1 by r square into partial derivative of r with respect to x. And just now we have calculated that the partial derivative of r with respect to x is x by r. So this is equal to the summation I vector, this is negative of x divided by r cube. And on the left hand side we are having this to be del xi. Now consider del square xi, that will be equal to del dot del xi, and this is equal to the divergence of del xi, right? Partial derivative with respect to x I vector plus partial derivative with respect to y j vector plus partial derivative with respect to z k vector, and its dot product with del xi. Del xi is what? This one. That is minus x divided by r cube I vector minus y divided by r cube j vector minus z divided by r cube k vector. And when we take the dot product of these two, we are getting partial derivative of minus x divided by r cube with respect to x plus partial derivative of minus y divided by r cube with respect to y plus partial derivative of minus z divided by r cube with respect to z. So writing this in a summation format, we get, so this is equal to summing up this in a one summation format. So this is summation partial derivative of minus x divided by r cube with respect to x. So this is equal to the summation. We have to derivate this with respect to x now. In the denominator we are having r the power 6, right? So writing the denominator first and derivating the numerator with respect to x, that is minus 1 minus writing the numerator which is minus x and managing these two, this becomes plus x into derivating the denominator, that is 3r square into partial derivative of r with respect to x. This is nothing but your x divided by r, right? So this becomes, if we separate the terms, we are getting minus 1 by r cube, right, plus 3xr square into x divided by r, and also there is r the power 6 in the denominator. So this is summation minus 1 divided by r cube and plus 3x square into, okay, here I am having r square, in the denominator I am having r the power 7. So this becomes r the power 5 Is it okay? Fine. Okay, let's open this summation. We are getting 3 divided by r the power 5 into x square plus y square plus z square, right? Minus the summation on 1 by 3. The summation on 1 by 3 becomes 3 divided by r cube, right? So this is equal to 3 divided by r the power 5, and this is your r square. It is given to us, minus 3 divided by r cube. So this is 3 divided by r cube minus 3 divided by r cube, that is equal to 0. So we are getting the value of del square xi to be equal to 0. Let me mark this as 2 and let me mark this as 1. The value of del xi and the value of del square xi, right? We are having these two values. Okay. Alright. Let me apply the second form of the Green's theorem now. We have the volume integral of phi del square xi minus xi del square phi, right, dv, and is equal to the surface integral of phi del xi minus xi del phi, and it's having the dot product with n vector ds. Now this del square xi is 0, right? So we are getting the volume integral of negative xi del square phi dv. This to be equal to the surface integral of, so this is equal to the surface integral of phi into del xi. What is del xi? We have taken xi to be equal to 1 by r. Yes, then del xi becomes del 1 by r. That is the gradient of 1 by r. So I am replacing del xi with the gradient of 1 by r or del 1 by r. Minus, again, this xi is 1 by r and this is del phi, right? And its dot product with n vector ds. On the left hand side also I am going to replace this psi with 1 by r. So I am getting the volume integral of, so this is the volume integral of minus 1 divided by r del square phi dv to be equal to the surface integral of phi del 1 by r, its dot product with n vector, minus 1 by r del phi, its dot product with n vector ds. Yes? Alright. And we can write this further to be as partial derivative of 1 by r with respect to n. Yes? Can I write like this? And also this can be written as partial derivative of phi with respect to n. So replacing this in the next step. So on the left hand side we are having the volume integral of minus 1 divided by r del square phi dv equal to the surface integral of phi. This is the partial derivative of 1 by r with respect to n. So partial derivative of 1 by r with respect to n minus 1 by r into the partial derivative of phi with respect to n ds. Hence, I am writing the surface integral first. This is phi partial derivative of 1 by r with respect to n minus 1 by r partial derivative of phi with respect to n ds equals to the volume integral of, I will take this negative sign outside. So this is 1 divided by r del square phi dv. So this is what is needed to be proved. So we have proved this result by using the second form of Green's theorem. Okay, thank you. Stay blessed.